galactic class 2 methanol mazes. This work is being supervised by Professor James Chibueze. As a disclaimer, I would also say my work is in collaboration with the Meerkat Galactic Plane Survey Consortium. And so I would like to acknowledge the consortium for allowing us to use the data to do this presentation. I would also say that because the work has not been published and there hasn't been any presentation so far, I would say kindly don't take a screenshot of the results. Thank you. Okay, so a lot of introduction has been given about massive stars, but I would like to just quickly add up that massive stars play fundamental role in the evolution of most galaxies. This is because they eject enormous amounts of radiation and energy and interact with their immediate environment, thereby causing the more stars to be formed. So this is just a schematic diagram of how massive stars are formed. So you have a cold compressed cloud, which now undergo accretion to form, it has smaller cores, and these cores are dense, and they usually have sizes of, they have sizes between 0.1 to 1 parsec. There are actually two models, two theories that have been postulated to explain how massive stars form. And these two theories are the core accretion and the competitive accretion. So with the core accretion, it is believed that a single core would undergo accretion, and depending on the rate of accretion, which should be higher, the core will now collapse to form a single star. But with the competitive accretion, the theory has to do with multiple cores colliding with each other. So the one that has the highest energy would collide with the other and then would form multiple stars. So the protostar that has enough mass would produce radiation called the UV radiation. And this UV radiation ionizes ambient medium in regions where they are formed. So this is how H2 regions are formed, and their classification is based on their sizes. So depending on the ionizing source, if the source is single, usually you have what we call the compact H2 regions. And those ones are also classified based on the evolutionary stages where they form. So because massive stars are deeply embedded, usually it's difficult to observe them in the optical. So we use other observational approaches, such as using infrared dust continuum, radio emission, molecular lines, and non-thermal emission, which is the methanol maser. So methanol masers are known to, especially the class 2 methanol masers at 6.7 is known to be exclusive to early massive star formation. So various surveys have been conducted, and out of about 1,085 regions have been discovered to have associated 6.7 gigahertz methanol maser. And out of the 1,085, 455 of them are known to have counterpart 12.2 gigahertz methanol maser. So a VLA follow-up observation was done to investigate 367 of the 455 methanol maser sites. And out of that, 279 were found to have associated ultra-compact H2 regions. However, no detection was made for 88 of the sources. This is because the sensitivity for VLA was 45 microjunsons. But with the sensitive meerkats, we've been able to explore 40 of these sources. And out of that, we found 28 detection. I wanted to talk about the observing strategy, but I think Wallace has talked about it. So I will just quickly mention that this observation was done at the L band, which has frequency ranging from 900 megahertz to 1.7. And then the central frequency was 1.2 gigahertz, and also 64 antennas were used, but most of the time, yeah. So to the results. These are the 28 sources that were detected to have the H2 regions. And out of these 28, we classified them based on the number of peaks as well as the size, which should be less than roughly 1 arcsecond. So for the compact sources, we were able to find 4 compact sources, and then the extended, those which have multiple peaks. I'll show examples later. Those ones were 14. And then we had 10 of the sources to be diffuse emission. So these are examples of the sources that we observed. So for G11.903, this is the position of the methanol maser. I hope you can see my mouse. But the blue cross is the position of the methanol maser. And also when you come to the second one, which is the extended source, if you compare the scale of the scale bar, you will see that these are really extended. They are larger than the diffuse, the compact sources. And then this is also an example of the sources we call the diffuse emission. So you usually find the methanol maser close to a continuum source, but would be at the edge of the source. So methanol masers are known to project on the H2 regions, which are usually found in the direction of infrared emission. So we compared the position of the methanol masers with the meerkat data, as well as the dust continuum from Atlas Gal. And then we compared it with the infrared to find if these are actually H2 regions based on the finding. So we find that most of the peaks where the crosses, the red crosses are, you will see the methanol, the meerkat position, and then the background is the glimpse. So you will find more of the glimpse coinciding with the peak position of the methanol maser, and also very close to the peak of the radio continuum. So this is also another example. This source is very faint, and we also compared the emission with the infrared. And then we tried to find high resolution data to also help us understand what is happening and also be able to make our analysis clear. So this data is an AMA data in band 7, and we obtained it from the AMA project code 2012-1, I've put it there. And we see that the position of the methanol maser also has a core, which is called MM1. So this confirms that it's an H2 region, and it's the molecular line that we detected from the ALMA data was the hydrogen cyanide. And this is the moment zero map, which gives the total intensity of the source. So in summary, I would say that we have looked at H2 regions that were previously, sources that were previously known to have class 2 methanol masers, but had no known H2 regions. And these sources, as I said before, had not been observed in L band. They have been observed at higher frequencies, but due to limitation in sensitivity, because most of them were done at millijansky level, and with meerkat, which is about 10 microjansky, it is 100 times better. So with that sensitivity, we've been able to detect 28 new H2 regions that are associated with the 6.7 gigahertz and the 12.2 gigahertz methanol lasers. Thank you.
Okay. We have time for questions for Mavis. Okay. I think we don't have any question both on the line and the people who are physically present. So we are going for our last talk for this session. And to present the last talk is Abdul Majid from Morocco. So 15 minutes including question time. 15, yeah. So I'll be one in this is Thank you very much.
Okay, thank you. Hello. My second presentation today is entitled Observational Study of RLA and SQT Variable Star at Oukenden Observatory in Morocco. My presentation will about I will introduce some brief general property of variable stars, and I will talk about the instrumentation that we use in our observatory. And finally, I hope that I have time to expose most results from RLE or RSQT. But the main goal of this presentation is for our colleague African that we can use small telescope to have a good result and to compare to height diameter telescope. That I will go to show you. So let me introduce some property variable brief. So variable star, why we study variable star? Because they have a standard candle for a distance and for study evolution of the universe. These amplitude and phase modulation are well known. The intensity of there are variation of their intensity. So variable stars research data can give us many information like mass, radio. It depends what we use, luminosity, temperature, and all. So I will not develop, but I can give you some basic bibliography. You can see that. So where we can find variable star in our standard laboratory universe for about 1 star, 100 million, some 100,000 is pulsating. So we have a lot of variable star to study. There is to define our field research. In this topic, I give variability of actually for variable star, and we are here. There's many variable. We are stars, pulsating stars, and we study this one, this category earlier, and for SQT arbitrary. So there is in this topic classical variation of intensity of luminosity of the star. There's periodic, and it depends for expansion or contraction of the star. So I should mention the evolution of the photometric curves, a phenomena which called the Blachko effect, referred to a long period modulation. It's a variation of period and amplitude in variable stars, as you can see here. And for example, for RRR star, the period for Blachko effect is about 40 days. So, which instrument we use to study this variable in our observatory? This is the second chapter. As you have seen this morning, we are here in the main dome in Observatory Kingdom, and our team make observation, make campaign from this dome, and we work in remote mode. In 2040, the team installed the measurement instrument of spectrophotometry. In 2040, we make in same times photometry and spectroscopy. So our combined at the same time photometry for the same target. And so we have data for photometry and data from spectrometry, and we combine to study all the phenomena. So there are two telescopes are mounted in equality front, and the spectrograph échelle was connected to the telescope by fiber optics. Now we have only a mid telescope, 20 each, and we developed to have the same manip like that, to use photometry and spectrometry at the same time. So we can add one small telescope on the mid, and we can get photometric data. Our methods. So through spectrophotometry, we aim to develop the field of pulsating stars, and we can explain some, especially atmospheric dynamic of high amplitude of RLA and RSCOT. So we work with the French colleague at OHP Observatory, and we have combined our result from OKMDN Observatory and their result from OHP in 1994 and until 1997, and our result complete until 2030 until 2020. So we combine this result to study the evolution of some particular profile like helium or hydrogen. So, summary, we have recorded more than 5,000 spectra, about 49 in France, and about 2,000 in observatory at Marrakesh. So let me give, yes, we have developed our new Python interface for analyze our data, because we have big data, so we need to analyze them, and we create this interface. let me go directly to the result of observation of RLE. So, but before, the context is our observation here were made to complete already established to study the atmosphere dynamic of the RRR star. So we can see in this table the principal main observation and of profile like of calcium, Balmer emission, doublum, helium, hydrogen, and more recently, we can compare the result with their Gili in 2013. He observed the first emission of helium at Hawaii Observatory, and in Oakhamden Observatory at the same year, we have observed the first emission, but in place the second emission that they can observe it in Hawaii with a great telescope. So let me show you this, the result. And here, the emission of helium observed by Gillet in 2013. And there is our comparison. Here in this photo, we compare our telescope 40-inch and Hawaii, and we have for the first time observed the second apparition of the helium. It was detected by our telescope 40-inch. So here in this graph, you can see the difference between two telescopes. One at Oakhamden Observatory, only 40-inch, and on the right, the Hawaii with 3 meter, 3.5 meter. So you can, here we can observe the second emission, and the right, we can observe it. Gillet can't observe this second emission. So let's see the efficiency of our observation in Oakhamden Observatory. We compare two with the result of Preston. In the left is our curve obtained in Oakhamden, and on the right obtained by Preston's. I have some, okay. So after we observe the first and second emission, we have studied the evolution of this emission in all phases of Blachko. And for the first time, that emission, we observe during the phase of the expansion of star is visible on various phase Blachko. After we compare our result to OHP observed in other years for 20 years, and you can see the curves. So a good summary for emission, we have observed the first emission, the second emission, and the first time we have detected the first emission in all phases of Blachko. So we do the same thing for H alpha, and let me show you this figure, and we compare here how can I, with small telescope and a good size, we can observe like a high diameter telescope. In the left, we have Oakhamden, and in the right, we have Hawaii. So we have studied the Balmer theory at Blachko phase, but I think I don't have time. Just let me show you just the beginning of study of the other star, the Earth-Scout. The Air Vectory type is Earth-Scout, and on the Air Vectory class, there is some property, and our height resolution, we have combined associate our height resolution spectroscopic with the Narval Observatory in the south in France, and we have practically made the same study as error, and we have developed a model to explain the dynamic of atmosphere of RQT. So we have published in January spectroscopic study of the atmosphere dynamic and pulsation of the observatory, and will be published. So let me show you that this graph, when they show our result combined to the narval in the reads narval our measure, and in green narval measurement. So we can, in conclusion of this study of two-star variable, that we prove that with small telescope we can really combine and obtain good and interesting results for the study of variable stars. We continue to carry out spectroscopic measurement combined in parallel with photometric measurement and we compare now to the data of test satellite. And we have a lot of night to analyze, and we shall present this result in the next conference in Spain. And now the goal, we hope to develop an African network telescope for study variable stars and use our data and to analyze with colleague Africans. And let me just tell you that we have a program with between European and African country that develop, which called Program European Horizon 5A, which will develop some telescope robotic. It will develop to photometry monitoring, and this program will enable to build in with six other telescope robotic for 6 country, African country. So thank you. Thank you very much, Edouard. I apologize.
Thank you very much, Abdul Majid, for the presentation. Now we have time for 1 or 2 questions. Wow. Start with the Alim.
Thank you for the nice presentation. My question is, you have been in this business for a long time using your telescopes. So are you sharing your data for the public, or you are only using for your own research purpose?
We want so to partage with our colleague, but until now we have only share with the partner, with the European partner. But if some African colleague want to share and study with us, you are welcome.
Okay.
Thank you for that talk, Abdel. I would like to make a comment. In doing my research for that review and annual reviews, I went back and read the primary literature. And the 1907 paper by Sergei Blachko was published under his name at the Moscow Observatory, but he is not the one who made the discovery of the variability in RW Draconis. In that paper, it's in German, you have to read it in German, he states that that was discovered by Mrs. Saraski. Now that was Lydia Saraskaya. And this is a very analogous situation to Henrietta Leavitt's discovery of the period luminosity relationship published by Edward Pickering. And so what I've suggested, and it's in the review paper, is that this should be known as the Saraskaya-Blachko effect. She's the one who made the discovery and got cut out because he got to publish under his name. Times have changed.
Okay, thank you for your information.
David?
I just wanted to ask, what is the resolving power of your shell spectrograph?
12,000 about, yes. It's,
then Mirana and
medium
finally will be
resolution.
James. Mirana and then James will be the last. And I think that will be all. We don't have anybody online.
Thank you. Yeah, that was really nice, nice talk. So I just wanted to comment that it would be good in Ethiopia recently, we are talking about establishing 7 principal research groups to strengthen a bit the research on the national level, especially for those people that are spread across the country, being totally alone at some of the universities. And the group in variable stars is one of them. So
Okay.
it would be good to get in touch between Ethiopia, Morocco, and your group. And then the Eshel spectrograph that is at Entoto that was never actually used is 37,000. And it would be good that we discuss then
Yeah,
between
sure.
the two groups what can be done.
Is it the same resolution?
37,000.
Okay.
37, yes. So it
Ah,
was
yes.
just a comment. Actually, my question was the same as.
So we can do a lot of things. Yeah.
Okay, and then,
So,
oh, okay, I thought that was James.
Okay,
hello.
thank you for the good presentation.
Thank you.
What is the cutoff V magnitude of the stars that can be observed spectroscopically using your
The
facility?
max.
The cutoff, the dimmest stars that can be observed.
The maximum of
The
mani-
lowest, yeah, the lowest.
Ah, yes. About with spectrograph, we have 9 magnitude.
Magnitude.
Yeah, magnitude.
Thank you.
9.
Okay, I think we are coming to the end of this session. So I want to thank all our presenters, Zubeda, Naomi, Willis, Mavis, and the Abdul Majid, and also the members who have been present both physically and online. We can clap
Thank you
for all
very
of
much.
us. So that marks the end of this session, and the next session will start after tea. We started 80 minutes late, but I think we were able to move up only 4 minutes past the time we are supposed to do. So thank you very much.
Thank you very much.